Hello friends, so today we will be looking at Hamming codes, which are an important category of uh, error correcting codes which are used in the data link layer of computer networks. So a couple of prerequisites first. So what is parity? So in a given bit sequence, if 1 occurs odd number of times, let's say 1 occurs 1 time or 3 times or 5 times, then its parity, the parity of the sequence is said to be 1. Otherwise 1 occurs even number of times and the parity is said to be 0. Okay, and in a bit sequence the bit can be either 0 or 1. That is the assumption. And let's say we have to transmit a message A. So we have to transmit this word A which we have. So this is the bit sequence corresponding to the ASCII capital A, 1, then 5 times 0 and then 1. So we have written it in our Hamming code form. So in our Hamming code form, the message bits go at the positions which are not the powers of 2. So 3 is not a power of 2, 5 is not a power of 2, 6, 7 are not power of 2, 9, 10, 11 are not powers of 2. So we take the bits one by one and stuff them at the positions which are not powers of 2. So we take 1, we put at position 3, that is represented here by M3. I have used M to represent that it is a message bit. And let's look at the bits which are at the positions which are power of 2. So 1 is a power of 2, 2 power 0, 1. 2 is a power of 2, 2 power 1. 4, 2 power 2. 8, 2 power 3. So these are the parity bits. We call them parity bits because they represents parity in some form. What form? I will explain now. So let's say we consider a bit M3. So we represent 3 in form 2 in the as a sum of powers of 2. So we represent it as a 2 plus 1. Similarly, we represent 11 as sums of powers of 2, 8 plus 2 plus 1. So what this means is the 11th bit will 11th message bit will contribute to the parity of 8th parity bit, 2nd parity bit and 1st parity bit. So 11th will contribute to 8th parity, right? 10th and 9th will also contribute to 8th parity because 10 is equal to 8 plus 2 and 9 is equal to 8 plus 1. Okay, so if it occurs, if the number occurs when we represent the bit as the position as a sum of powers of 2, that means that it will be affecting the parity bit at position 8. So P8 will be affected by M11. So that's why it's 1, because only M11 is affecting it. M10 and M9 are stale because they are anyway 0, so they will not affect the parity. Now M7, M6, M5, then P4, so they are all 0, so they will not affect anybody. P4 cannot be affected by 3 because 3 is lower, so the sum 4 is not occurring. In this sum 11's representation also 4 is not occurring, so nobody affects the parity of 4, and hence the parity of 4 is 0. 3 is a message bit 1. Again 2 is a parity bit, so 2 will be affected by 11 as well as 3 because it occurs in both the representations. So now both of them are ones. This is also 1 and this is also 1, so 1 occurs 2 times. So for P2 we consider 1 2 times, that is even number of times, hence the parity is 0. Again for 1, that is P1, it is occurring 2 times, that's again a parity of 0. Let's say we transmit it on a channel which is noisy, hence causing a 1-bit transmission error, and flipping the M5 bit and making it a 1. Okay, so what we do is, on the receiver end we take the bits one by one and compute the parity again, but this time the difference is that we consider the check bits also. So let's say we compute the parity of this one, 8th bit. Okay, so we include this one also, we include this one also, and the parity comes as 0. Okay, and now the 5th bit is 1, so we have to write 5 as well. So we write 5 as 4 plus 1, so 4 plus 1, right? Okay, now we compute the next parity, the parity of this bit, which is coming as 1, because 4 is present in only 5th one, that's all. 5 is the representation only, 4 is present, so the parity is coming as 1. Again we compute the parity of this one, this comes as 0, and finally we compute the parity of the first bit, that is P1, and 1 now comes in 3 representations, this one, this one and this one, so the parity comes as 1. So that's the final computation of parities. If all of them comes as 0, that means we are good, we have received the exact message which was transmitted. But if some of them are 1, then we convert it into decimal. Converting into decimal gives us 5. So we know, and the Hamming code is designed in such a way that the after conversion what we get, that is the number of the bit which was flipped. Magic. We flip the 5th bit to get this message. Now here 0 comes, this one, very good. We discard the bits occurring at 2 powers position, so 2 keep bits because they are check bits to get our message. So we discard this one, we discard this one, 1 2 4, this one we discard, 5 6 7 8, this one we discard. So 1 0 0 0 0 0 1, which is A, the sender has sent A. So the receiver has finally got the correct message. So this is Hamming code with a distance of Hamming distance 3, which means it can detect up to 2-bit errors and correct up to 1-bit error, as just we have demonstrated how to correct a 1-bit error. So thank you friends.